Greetings of the day, dear students. In this video, we are going to discuss about the efficiency of three-phase induction motor. Here, how the total losses are classified in the induction motor, what are the different losses we are having, what are the different terminology we are having, right? And what are the important formulas we are having, and finally what is the formula for efficiency. All those things we are going to discuss in this video, right? So dear students, with respect to the efficiency, right, eta is equals to the output power divided by input power. Now for any given system, whatever the value of input we have given, we cannot get it the entire power as an output. Obviously there will be some amount of losses in the input, right? So here obviously our output will be nothing but the input minus losses, input minus losses by input. So with respect to the losses for a three-phase induction motor, what could be the different losses we are having? We will be classifying it as some fixed losses and variable losses, fixed losses and variable losses. As we are having a stator part and also we are having a rotating part. For the stator, where we have given a three-phase supply, right? Now out of the given electrical input, because of the winding present, and there will be some amount of copper losses, and also there will be the core losses. So obviously there will be the losses in the stator and rotor, right? Now as we are having a rotor and rotating part, and we used to have some mechanical losses and also some friction, brushed friction losses. So these are the different types of losses. Out of these we can simply say it as fixed losses and variable losses. With respect to the fixed losses, stator and rotor core losses, mechanical losses and brushed friction losses will be the fixed one. Now depending upon the amount of the load and current drawn by the motor, so because of the current drawn by the motor, where the value of current will be changing, I square R losses also will be changing. That is the reason why we used to have stator and rotor copper losses as variable losses. These losses are variable in nature because of the if any change in load is there, obviously the current drawn by the machine will change. Once the current drawn changes, I square R will change. So these losses will be variable, or which depends upon the load. If load changes, I square R losses also will change. But whereas stator and rotor core losses, mechanical losses and brushed friction losses will be constant, right? Here out of the electrical input power, let me denote P in as electrical power supplied to the stator of the three-phase induction motor, and where VL is the line voltage supplied to the stator of the three-phase induction motor, and IL be the line current. So from our previous basics, the input power, the three-phase input power is given by √3 VL IL cos phi. Now out of this much input power, given input power, right, this entire thing will not go to the rotor, right? So here this input minus stator losses will be the power input to the rotor. This is very, very important. Simply to say, the rotor input is equals to the electrical input power minus stator losses. What are the losses that occur in stator? Those are to be subtracted. Now this is the input. Now this entire input will not be developed as a output across the shaft. Now again there will be losses at the rotor also. Those are to be subtracted. Let PC be the rotor copper losses, because rotor is also having winding, field winding is there. So obviously we will be having rotor copper losses. Let I2 be the rotor current, and the resistance of the rotor be R2 be the resistance in the rotor. Now the PM be the gross mechanical power developed. PM is the gross mechanical power developed. So here PC, the rotor copper losses will be equals to the 3 times I2 square. R2 already we have defined. I2 is the rotor current, R2 is the rotor resistance. Now the mechanical PM is the gross mechanical power developed will be equal to P2. P2 is already defined, rotor input minus rotor copper losses. This is again very, very important. I repeat again, dear students, out of the given electrical input power minus stator losses is the rotor input. Out of this rotor input, P2 minus PC, rotor copper losses will give you the PM value, gross mechanical power developed. But that entire gross mechanical power developed will not be available at the shaft. From this PM, again we have to subtract the mechanical losses. That will be our final output. So in the efficiency formula, efficiency eta equals to P out by P in. The output is the mechanical power, the input is the electrical power. P in already we know, root 3 VL IL cos phi. Now P out is given by PM minus mechanical losses. So finally the efficiency eta is equals to the output by input. Now this eta, power developed at the shaft divided by electrical input to the motor, eta is equals to the P out by P in. So this is how we can calculate the efficiency of 3-phase induction motor. I repeat again, dear students, whatever the input is given, that will not come out as an output. Definitely there will be the losses. So obviously input minus losses will be equal to the output. Now the losses are classified as fixed losses and variable losses. Out of these fixed losses, stator and rotor copper losses, mechanical losses and brushed friction losses are treated as fixed losses, and the stator and rotor copper losses are treated as variable losses. Variable losses are due to the change in the load, right? If the load changes, the current drawn by the machine will change. Once the current changes, I square R also will change. That is the reason why we can treat them as the variable losses, right? So this is how we can find out the efficiency of a 3-phase induction motor, right? Thank you.